Welcome to day 1 of beginning algebra, number sets and structure of algebra. Important vocabulary. I really encourage you to start thinking of algebra as a language. It has its own alphabet, vocabulary, and sentence structure, and indeed it is a language. So let's begin. These are words that are going to be very important as we travel along. Variable, constant, expression, equation, inequality, and set. Okay, so what I'm going to do is just tell you the definition. Feel free to write it down, and then perhaps run you through some examples. Okay, so let's start off with variable. Variable is just a symbol that can vary in value. For example, so I'll just go off on the side here. X, alpha, lambda. Often we use those Greek letters. Okay, Z. Okay, so it could be a Roman alphabet or a letter from the Greek alphabet, but it's a letter that in essence represents a number, but it could, no one knows the value of that letter until you solve, say, an equation, something like that. Okay, a letter that could take on many values. Constant. A constant is a symbol that does not vary in value. It has one value. Okay, so constant, like what? The number 2. That's a constant. Pi. Even though pi is a symbol, it's a constant because it represents 3.14. Okay? Approximately. So it doesn't change. It is what it is. It's 3.14. And, 3.2. That's a decimal, but, it's a constant. So it does not vary in value. Okay? Expression. Now let's head into expression. Expression is a constant or a variable, or any combination of constant and variables and n along with arithmetic operations that describe a specific operation. So I know that's a lot to say, a mouthful, but example. 4x minus 5. And there you've got the number 4 attached to a letter, which is by multiplication. So 4x, that means 4 times x, and then minus 5. So you actually have two operations there. You have 4 times x minus 5. So you have a coefficient, a number, attached to a letter, and then an operation, and then a 5. So a combination. Or, pi r squared. You might recognize that as area of a circle. So pi is obviously a mathematical constant, but here it's being attached to r squared by the operation of multiplication. Okay, so that's just an expression. It's not an equation. It does not contain an equal sign. So that kind of takes us into the next realm there. Equation. Equation is a mathematical relationship that contains an equal sign. So, all right, 2x minus 7 equals 5. So that's a mathematical relationship, but you're noticing the equal sign. Now it's an equation. Okay, inequality. Let's take a closer look. So we want to really inspect each one of these words. Inequality is a mathematical relationship that contains an inequality symbol, such as a less than, a greater than, a less than or equal to, or a greater than or equal to symbol, or not equal to symbol. So examples of that might be, okay, 2x is greater than 7. That's an inequality. Or, 3x minus 1 is less than or equal to 9. That's an inequality. So it's a relationship that contains an inequality symbol. So what I'll really remind us of here is, note to self, be on the lookout for this symbol, the not equal to, this one, this one, this one, and this one. So again, this is your not equal to, your greater than, your less than, greater than or equal to, less than or equal to. So if it contains one of those symbols, you have yourself an inequality. Okay. And now set. Set is just a collection of objects. So say we're interested in the set that contains the first 3 letters of the alphabet. We'd usually denote that with a curly brace. So curly brace, A, B, C. So just a collection of objects, usually denoted with curly braces. Forgive that curly brace there, it looks a little strange. Separated with commas, so the elements are separated with commas. And that could be a collection of any objects in the whole. It could be a collection of the set of even numbers, the set of odd numbers, whatever set of natural numbers. And we're going to start taking a closer look at sets right about now. Let's take a moment to zoom in and on sets and really sort of dissect them and think about them a little more deeply. The real number line. If we travel along this real number line, we're going to encounter all kinds of numbers, and that belong to the set of real numbers. So, but notice that all the numbers that live on this line, they're not all integers. So, most people when they think of the number line, they think of 0, -1, -2, 1, and 2. But not all the numbers that are on this number line are integers, right? So like what is 2/3? It's not an integer, it's rational. So mathematicians decided to classify sets of real numbers. So what I'm going to do here is make a little drawing for you. First, let's think of sort of the evolution. First, there were the set of natural numbers. I like to think of them as the caveman numbers. So that you count on your fingers, right? 1, 2, 3, all the way on out to infinity. So those are your natural numbers, the set of natural numbers. Okay? Then you say, okay, well, hey, 0 is not on that list. So then comes into play the set of whole numbers. So we'll describe all this language that's in your text. So then we have the set of whole numbers, and that would be 0, 1, 2, 3, etc., all the way on out to infinity. But notice, you still don't see any fractions or any decimals or any negative numbers there. So then we say, okay, what about when -1 comes onto the scene? Because obviously humankind realized that there are applications for negative numbers, right? So -3, -2, -1. 0, 1, and 2, right? And 3, all the way on out. So what can you say, what can we call those? All right, well, that's going to be your set of integers. And you say, all right, well, notice that there still aren't any decimals in there. Like, what about 1.7, 1.82, -1.4? Say, okay, well, we're going to call those something. So rational. So we're going to say, all right, rational. A rational number is any number that can be written in the form P over Q, where Q is not equal to 0. So basically a rational number is a fraction. Okay? So all of these fall under the umbrella of rational, meaning if you're natural, you're automatically rational. And if you're a whole number, you're automatically a rational number. And if you're an integer, you're automatically a rational number, right? So because all of these whole numbers, 3 can be written as 3 over 1. So it can be written as a fraction. Rational just means it can be written as a fraction. So you can think of rationals as fractions. Then you say, all right, well, I like to think of rationals also as repeating or terminating decimals. Say, all right, well, what about, is there such thing as something that is a non-repeating, non-terminating decimal? So I'm going to make this umbrella a little bit bigger here now. This red one, all of these fall under the umbrella of the set of real. So these are real number classifications, okay? The big red umbrella there is the set of reals. And you say, well, is there such thing as a non-repeating, non-terminating decimal? Well, sure, like the transcendental numbers, like pi and e. So numbers like pi and e that are non-repeating, non-terminating decimals, we're going to put them off, and I'll make another color for that, blue, off in their own little realm. And what are they called? Irrational, because they cannot be expressed as a fraction. So irrational. Some people say, well, yeah, pi is 22 over 7. Well, that's just an approximation. It isn't really 22 over 7. So pi can't be expressed as a fraction. Okay, hope that helps with your number sets. Now, just to make sure you were paying attention, though, I'm going to do a quick little quiz here, example, just to see if you know. True or false? 0 is a natural number, or belongs to the set of natural numbers. And if you're trying to look at your diagram, you say, aha, the natural numbers do not begin with 0. They're 1, 2, 3, 4, 5, all the way on out to infinity. So 0 is not a natural number, so this is false, right? 0 is a whole number. Let's try another one. Make sure you're getting comfortable with the language. True or false? Pi is rational. And you say, no, that's false, because pi is irrational. It's a non-repeating, non-terminating decimal, and it can't be expressed as a fraction. Okay, so we're going to play more with these number sets in a moment. All right, changed my mind. Decided to do, just to make sort of an all-encompassing example here with number sets, just to really solidify things. I'd like you to express the set of odd natural numbers greater than 7. So now let's really make sure we're nailing down the language. So the set of odd natural numbers greater than 7. And we want to just kind of express that using set notation. So you think about natural and you say, okay, if they're natural, they're not decimals or fractions. So, and greater than 7, so you can't actually include 7. So what would that set look like? Okay, so curly brace. You say, can I use the number 8? No, 8's an even number, so it couldn't be 8. What's the next odd natural number bigger than 7? Say, okay, 9, 11, 13, 15. So there we are, we're looking at all the odd natural numbers bigger than 7. That's an example of how one has to read the language of math and translate, really. All right, hope that helps.